The fragments of the Titan submersible, recovered from the ocean floor in 2023, tell a chilling story that safety, despite formal promises, doesn't always prevail over production. Today, we're grappling with the stark reality presented in an analysis titled Zero Risk, Illusion or Legal Obligation, which highlights how commercial pressure in physically ruthless environments like the abyssal depths or the vacuum of space forces regulations to confront an uncomfortable truth. Exploring the unknown inevitably requires accepting a level of risk no law can eliminate. Clara, how does this tension between technological progress and human cost play out in the underwater and aerospace sectors?
The core issue is that these two industries operate at the absolute extremes of physics. On one hand, you have the crushing pressure of the ocean trenches. On the other, the immense energy needed to escape Earth's gravity. The conflict between those who design these vehicles and those who create the rules has never been more intense than now, especially as private companies increasingly replace government agencies. They bring with them a corporate culture that often clashes with traditional engineering caution.
This dynamic isn't new. It hasn't just emerged with contemporary tech billionaires. If we look at space exploration, institutions have often painfully learnt what happens when the schedule or production takes precedence over safety. NASA, for example, offers perhaps the sternest warning.
The quintessential case study is the Space Shuttle Challenger disaster in January 1986. Engineers at Morton Thiokol, the contractor for the solid rocket boosters, were fully aware that the seals, the famous O-rings, lost their elasticity at temperatures near zero. The night before the launch, there was a dramatic teleconference where engineers like Roger Boisjoli pleaded with management to postpone the mission due to the exceptionally cold weather forecast in Florida.
Yet, the launch went ahead. Subsequent investigations revealed that NASA was under immense political and media pressure to maintain tight schedules. There was even pressure to coincide the flight with the President's State of the Union address. Managers simply instructed technicians to disregard the data and prioritize business needs.
The consequence was tragic. Incandescent gases escaped from the seal, stiffened by the cold, and the Challenger exploded 73 seconds after takeoff, killing all 7 crew members. That event fundamentally redefined risk management in aerospace. It demonstrated that the greatest danger lay not in the hardware itself, but in organizational communication failures and the prioritization of scheduling over safety.
That's when the illusion of absolute control truly shattered. It introduced a fundamental concept that modern regulations now try to apply in high-risk sectors. The idea that risk must be reduced to the lowest possible level while still acknowledging that it will never be truly zero.
In engineering and regulatory fields, a principle called ALARP is used, an acronym for as low as reasonably practicable. The International Maritime Organization, for example, consistently applies this principle to regulate safety at sea. Regulations do not claim that the probability of a maritime accident must be zero. Instead, they demand that operators demonstrate, through rigorous mathematical models and cost analysis, that they have implemented every risk mitigation measure that isn't disproportionately expensive or complex when compared to the benefit gained.
Applying ALARP to a cargo ship or passenger ferry makes practical sense, but surely when we're descending 4,000 meters deep to explore wrecks or untouched seabeds, the tolerance for error virtually vanishes. From a technical perspective, what kind of challenges does the engineering of abyssal submersibles face?
The technical difference between space and the deep ocean surprises many. Data confirms that the ocean floor is a far more hostile engineering environment. In orbitable space, the pressure difference between a spacecraft's pressurized interior and the external cosmic vacuum is only 1 atmosphere. The main danger in spaceflight lies in the launch phase and thermal re-entry. In the deep ocean, however, at 4,000 meters, a hull must withstand a force of about 400 atmospheres, meaning tons of weight for every square centimeter.
If a partial depressurization occurs in space, as it has in some missions, the crew often has time to don emergency suits and isolate compartments. That implies a degree of control. But what happens with a structural failure at oceanic depths?
If there's a structural failure at oceanic depths, the implosion occurs in fractions of a second, literally faster than the human nervous system takes to register a pain signal. This is precisely where certification regulations become the dividing line between life and death. The underwater vehicle Alvin, operated by the United States Navy, has completed thousands of dives in total safety. Its titanium cabin sphere, several centimeters thick, undergoes rigorous testing to withstand pressures 1.25 times its maximum operational limit. There's a Navy protocol, P9290, which strictly regulates every aspect of design in deep waters, relying on classification societies like the American Bureau of Shipping to verify materials.
Yet private industry has found ways to circumvent these established standards. In the case of the Titan submersible, his creator deliberately chose to bypass naval classification agencies. His public argument was that the certification process, which requires years of slow and meticulous testing, would stifle technological innovation. But what were the engineering consequences of that decision?
Stockton Rush chose to use carbon fiber for the pressure hull, paired with titanium domes. Carbon fiber is exceptional for tension, which is why it's used in aerospace, but it degrades unpredictably under continuous cycles of extreme compression. Rush claimed an internal acoustic monitoring system would warn the crew of imminent material delamination, giving them time to resurface. Experts in the field knew this approach was fatal. When carbon fiber begins to fail under such pressure, the implosion is almost instantaneous. The acoustic sensors only tell you that you are about to die in a few milliseconds.
This philosophy of aggressive innovation, which seems to prioritize experimentation over certification, feels like a direct export of the IT mentality, the concept of moving fast and breaking things to learn. But when failure implies the loss of human lives, the lack of mandatory regulations becomes an unforgivable loophole. How does this mentality clash with the private aerospace sector, where we see companies like SpaceX adopting similar development methodologies?
SpaceX uses a rapid, iterative development approach that effectively involves the loss of prototypes during testing, as we've seen with the spectacular explosions of their Starship rockets in Texas. However, the regulatory dynamic is different. The government oversight body, the Federal Aviation Administration, or FAA, requires detailed assessments of environmental impact and the safety of surrounding areas before every launch. When debris from an experimental launch scattered over protected natural areas, regulators blocked subsequent operations until corrective measures were implemented.
So the FAA intervenes heavily to protect the environment and the uninvolved public on the ground. But when it comes to paying passengers boarding these commercial vehicles, does the agency's approach change radically?
It absolutely does. Regulation seems to take a step back so as not to hinder the nascent space tourism industry. The United States Congress has established a regulatory learning period, which has been extended several times. This moratorium prohibits the FAA's Commercial Space Transportation Division from imposing strict safety requirements for the design of vehicles intended for passengers. Currently, federal law relies on the principle of informed consent. Passengers, legally defined as spaceflight participants, must sign formal documents explicitly acknowledging that the U.S. government has not certified the spacecraft as safe.
So the entire responsibility for risk acceptance is transferred from the government designer to the private consumer. This informed consent model might work for wealthy adventurers willing to bet their lives, but it raises enormous ethical questions if we consider these companies' ultimate goal: mass space transport and the establishment of extraplanetary colonies.
The transition from high-risk experimentation to mass commercial transport requires a paradigm shift that historically has always come at a high price. Commercial civil aviation has reached its current level of obsessive safety precisely by methodically analyzing past tragedies and imposing inflexible regulations. Researchers from organizations like the Aerospace Corporation have developed mathematical models to predict failure rates for future commercial suborbital flights. But the statistical sample of actual flights is still too small. We are effectively building an industry based on dozens of test flights, while commercial aviation relies on billions of consolidated flight hours.
This tension between commercial deadlines and rigorous oversight isn't limited to experimental frontiers. The traditional aviation industry has provided us with a devastating example of how production pressure can corrupt the regulatory process from within. The Boeing 737 MAX disaster had nothing to do with exploring extreme environments, but was entirely driven by the need to protect market share against a rival company.
The 737 MAX case highlights the extreme dangers of practical deregulation. Boeing was desperate to bring an aircraft with larger, more efficient engines to market to compete with the Airbus A320neo. To avoid having to subject pilots to expensive and lengthy simulator training, they designed the new plane to behave exactly like the old models, implementing corrective software called MCAS. This system was supposed to automatically lower the nose of the plane under certain aerodynamic conditions to prevent a stall.
The tragic paradox is that the FAA, to accelerate certification times, had delegated much of the review authority to Boeing's own engineers. The regulator effectively surrendered its role to the controlled entity. How did this corporate pressure manifest in fatal engineering decisions?
Corporate pressure directly led to fatal engineering decisions. The MCAS system relied on a single angle of attack sensor, violating basic principles of aeronautical redundancy. Furthermore, Boeing removed information regarding the MCAS system from pilot flight manuals, considering it superfluous. When faulty sensors abnormally activated the system on flights in Indonesia and Ethiopia, pushing the planes downwards, the crews found themselves battling against invisible software whose existence they were unaware of. Those 346 deaths are the direct result of a regulatory system that permitted production goals to evade fundamental safety requirements.
Regulations are often perceived by corporate management as bureaucratic friction that slows progress or erodes profit margins.
But these compliance manuals aren't born from a desire to complicate engineers' work. Every rule, every redundancy requirement, and every inspection protocol represents a lesson hard-won from a previous disaster. There's an open debate about whether an excessively preventative regulatory approach would perhaps have entirely prevented the triumphs of the Apollo era.
The Apollo program certainly operated with risk profiles that contemporary government agencies would find unacceptable. During the lunar landing design phases, models indicated frighteningly high probabilities of crew loss. However, the context was dominated by an existential geopolitical imperative of the Cold War, which American society and its leaders considered sufficient to justify the risk. Today, the dynamics have changed. Risks taken by private corporations are driven by commercial imperatives, financial gain, or personal prestige. Developing regulations that prevent disasters doesn't mean stopping exploration, but preventing private ambition from turning the crew or passengers into expendable guinea pigs.
And here another jurisdictional challenge emerges. In space, there's the Outer Space Treaty of 1967, which makes national governments responsible for the activities carried out by their private actors beyond the atmosphere. In the deep ocean, however, a near total legal vacuum reigns. If you operate in international waters at 4,000 meters deep, you're essentially outside the reach of any national oversight agency.
International maritime conventions are structured to handle surface ship traffic, fishing, and the exploitation of seabed resources, but they're entirely inadequate for monitoring the use of experimental vehicles launched from motherships flying flags of convenience. There is no police of the abyss. This regulatory black hole is precisely what permitted uncertified operations to repeatedly dive into an environment that tolerates technical errors even less than outer space.
Analyzing these narratives, from the cold that destroyed the Challenger's O-rings to the failure of carbon fiber in oceanic depths to the faulty sensors of modern airliners, a universal lesson emerges. Regulations aren't just about the thickness of metal alloys or aerodynamic certifications. They serve, above all, to create and defend an organizational system where the voice of a technician who detects an anomaly has the power to stop an entire industrial apparatus without fear of corporate retaliation.
High-reliability systems are based on the institutional capacity to welcome doubts and stop operations when anomalies emerge. Rules serve to protect those who have the courage to say that the vehicle isn't ready to depart. Without the protective umbrella provided by independent and rigorous oversight, the natural pressure towards profit and rapid results will relentlessly continue to erode safety margins. The underwater and aerospace sectors demonstrate daily that pushing human presence beyond natural boundaries involves extreme engineering risks. But regulations remain the only rational tool to separate thoughtful exploration from catastrophic gambling. Managing the inevitability of risk doesn't mean being able to erase it, but ensuring that every single operational decision is made by ruthlessly questioning scientific data before consulting financial projections.
Share this episode with those who love to explore the intersection of engineering, ethics, and the price of human progress.